Now in this session we will show that if you take an arbitrary wave function within the context of a measurement of observable A, big A, as we're talking about three sessions ago. So within that context, then you can express your general wave function in terms of a weighted sum of wave functions which serve as a basis. Remember, a basis is a set of wave functions such that you can weight them, multiply them by complex numbers, C, sum them, and that weighted sum then approximates closely, or as accurate as you like, in a Fourier analysis type reasoning, your general wave function. Okay? And then if you perform a measurement of observable A, the probability that you will get a result, let's say little a, I, which would correspond to the wave function psi I, probability of that happening, of getting the measurement result a, little a, I, is Ci squared, where Ci is the coefficient in your weighted sum. Okay, so we'll now show you that in the context when the observable is energy, when your big A is E, you're talking about energy, measurement of energy, that the C in your weighted sum, the C squared, actually gives the probability of measuring that particular energy value, EI, the ith allowed energy E. Okay, so here's your general superposed state. So just some general state. These wave functions here are your basis set. They are orthonormal, so you can use them to create a weighted sum to express any function that you want in the context of measuring the observable big A, whatever big A is. All right. Now, in the context when A is the energy, you measure the energy. Your wave function then collapses to the wave function whose energy value you actually measured. Say you got EK. Say you got the kth allowed energy. That was when you did the measurement. That was what you actually observed. Okay. So therefore, this is no longer appropriate. It collapses to psi k. Right? So we'll collapse to psi k. All right. So what we're going to do now is we're going to assume, we postulate. We just think it's true, and it's a postulate. You assume that it's true, and you then logically deduce its consequences, and then you can test those consequences with an experiment and see if they work. Well, here we're doing kind of theoretical tests. So if these wave functions here now are eigenstates of your Schrödinger equation, where your eigenvalues are energy values, allowed energy values, here. So your Schrödinger equation then you can look at as an eigen equation, okay, where these wave functions are then eigenstates, right? They are eigenfunctions, eigenstates, same thing, right? Then these C's here give you, if you square them, that gives you the probability of obtaining this energy. Right? Now, if that's true, and we're putting it here as a postulate, this is like a particular case of what we had 3 sessions ago, where we're dealing with the general case for observable A. Here it's a more particular case. The observable is energy. Big A is now E, energy. So to persuade you that this probabilistic interpretation, meaning the probability of getting the result EK is CK squared. Okay? That's it. So so we assume it's true, and we just postulate it's something we think it's true. So, and then we start drawing conclusions from it, and that's what we're doing now for the rest of this session. Okay, so assume then the probability of measuring EK is CK squared, where CK is just one of your coefficients here in your superposition, right? So, for example, let's try to find the average value. Say you perform a zillion measurements on the same system. You're similarly prepared again and again and again as accurately as you can. You set up the same system again and again the same way, and you perform a zillion measurements. What's the average energy that you would expect? And we'll show that what you expect, based on this assumption, is what you actually get using the Schrödinger equation. So it's a kind of theoretical justification that this idea, when you square the Cn or Ck, that gives you the probability of finding that energy. All right. Well, let's find out what we should get, and then we'll solve the Schrödinger equation in a sense to get the same result. So that confirms, if we do get the same result, that confirms this idea that squaring the C gives you the probability of measuring that energy value, EK. All right. Well, what is the average of E, the average energy? Well, can you see it's just the probability of measuring E, the nth value of E times the E of n? Is that? I mean, I could put anything here. I could put x in here, and the average value of x, whatever x is, would be the probability of getting x. When you measure it, you get that value times x. Right? This here is just statistics. This is just statistics and pretty well common sense, right? So the average of some value is just the probability of getting that value times the value itself, summed over all possible values. Right? So, all right. Well, in this case, now our postulate is that the probability of observing energy EM is Cn squared, where Cn is it's one of these. If you're talking about the kth energy here, then this would be Ck. Right? So the average energy would be this. That's what we'd expect. Okay. So from now on, in fact, this last line here, the first line of our confirmation proof, if you like. So what we're doing now is we're taking Schrödinger's equation, and we'll try to get this result using rewriting. Now the angular brackets, remember, is just find the average value of, right, or the expected value or expectation value. Expectation is a better term. Expectation value. Expectation value. That just means average value, same thing, right? So now the average value of E is that's your Born interpretation, right? The square, the probability of measuring something. In this case, it's not position, so we haven't got an x here, we've got an E. So, and these wave functions are about the E observable. So in the context of wave functions about energy, okay? So we can rewrite this as this, and rearranging slightly, put the E in the middle. Doesn't really change much, does it? depends. Well, okay. For this case, E is just a scalar. Is that right? Yeah. So it doesn't matter where it is. Okay. So rewrite this as this, and now, but E psi is in a sense the right